Today with 3 questions on the Socrative app, and the first one there is or has been waiting for you, and reads, and blank process is one that absorbs heat energy from the surroundings. Consequently, the temperature of the surroundings will do what? So we'll check out our answers here. If you want to get your answer in, do so now. Count down. 5, 4, 3, 2, 1. Correct choice is A. An endothermic process is the one that absorbs energy from the surroundings. Consequently, the temperature of the surroundings will decrease. Let's check out the second one. And blank process is one that releases energy to the surroundings. Consequently, the temperature of the surroundings blank. What will happen? So we'll get our answers locked in here, please. Count down. 5, 4, 3, 2, 1. All right, so we got perfect on that one. Let's get those into the record for the day. Again, the first one was endothermic. Again, the temperature here is going to do what? Decrease. And that means that an exothermic process, I'm going to try to help you with the colors a bit. An exothermic process is one that releases energy to the surroundings. Consequently, the temperature of the surroundings will increase. Now, part of the reason why I have bolded some of these words is that these are the ones that we need to look at that have some importance, particularly when we talk about absorbs from the surroundings and when it releases to the surroundings. And the reason for that is because when we are going to be looking at processes, we're going to be looking at 2 key components. We are going to be looking at the system and the surroundings. Now, ultimately, what we want to do is we are going to want to describe what happens to the system in each of these processes. And so the system is going to be the part that includes the reactants and the products. So again, ultimately, what we want to figure out is what's happening to the system. And the system is going to be the part then that contains the reactants and products. However, you and I are not a part of the system. You and I are part of the surroundings. And so we say that the surroundings then are basically anything that is in the vicinity of the system. Now, where this is going to prove challenging for some of you is this. Because whatever you and I observe, and you and I are part of the surroundings, whatever happens to the surroundings is going to be exactly the opposite of what happens to the system. So if you and I, or the surroundings, we have energy that's removed from the surroundings, that means that the energy has gone where? Into the system. And if energy leaves the system, that means it has gone into the surroundings. So if the temperature of the surroundings has increased, that must mean that the energy has done what in the system? It has decreased. So again, if the energy of the surroundings has increased, that means the system has decreased in energy. And likewise, if the energy of the surroundings has decreased, that is, if the temperature of the surroundings has gone down, that must mean that the energy of the system has increased. And for many, that is kind of counterintuitive, because if we go back and look at the demo we passed around the other day, you might remember when we combined together the barium hydroxide and the ammonium chloride, that was one where the temperature got really cold. Well, if we observed it really cold, that process again is one that was endothermic. We could tell it was endothermic because the surroundings, the flask, whatever it was, got colder. And because it got colder, that means that the energy came out of that flask, and we perceive that by us touching the flask. that the energy had gone out of the flask and into the system or the reactants. So again, that is one then that is an endothermic process. And so we want to get to the point at the end where we're not flipping coins or we're trying to decide is this endothermic or exothermic. But what we always have to remember is that you and I, again, are always a part of the surroundings, but in the end, we don't care what happens to the surroundings. In the end, we're going to want to tell what happens to the system. And it's always going to be just the opposite of what you and I observe because, again, we are part of the surroundings. And that's the place where, again, students have trouble with some of this. Any questions with that? Okay, next thing we're going to look at is we have a demo. And in this demo, I'm going to take some copper, and we just want to verify that the amounts are right. I did pre-weigh these, but just so to make sure that their mass hasn't changed over the last couple days. We'll check this out real quick, and maybe our camera isn't going to work anyhow. There we go. And I don't know why it always takes this thing so long to focus. But we are going to put this copper into some water. Come on, will you please? Again, I have no idea why this camera does that. Okay, well, I think then you're just going to have to trust me, and we'll wait and see if this thing will actually focus. Can we focus? Auto, near, far, nothing. Doesn't want to focus at all today. All right. Well, then we're just going to put it on here, and you'll have to trust me. We will look at the exact mass here. The exact mass is 113.78 grams. And you can write that down. And then we're going to put 113.78 grams of water into this cup. So we've zeroed that balance out. It does disturb me though that this thing doesn't work. Okay, nothing. Okay, well, whatever. So 113.78 is what we're putting in. So we'll add it here. Oh, forgot to do something. I'm going to warm up this copper and put it into this beaker of water. And I need some tongs. Let's see if I took the tongs out. Here they are. We need to lay the copper down in there. We'll put another piece of copper in. And we're going to get that warmed up. So we're at 77.74 grams right now. And we're going to bring this up to, how much was it again? 113.78. Okay. So right now we're at about 100. Okay, and that's going to be close enough. I have 113.94. So again, that's why in the particular problem we looked at it being 114. Because at least the three significant figures, the results on this will be rather consistent. So now the next thing I'm going to do here is take some temperatures. So taking some temps. I've put these up on Logger Pro, and we'll go ahead and measure the temperature of the water. Now you're going to use the exact temperatures that we have here. On the Socrative app, I did approximate these. So let's just check these temps really quick. And I came in this morning to measure the temps just to see about where our boiling point was and where the temperature of the water was. It looks like I was pretty darn close. So it looks like the temperature of our water here is 22.1 degrees Celsius. And then the copper. Now the copper that's in here, how should the temperature of the water in here compare to the temperature of the copper? How should those two compare to each other? Should be the same or should they be different? Same. They should be the same because heat energy flows until the temperature on each side is identical or equal. So if I come back here now and measure the temperature of the water, and I don't know, I keep losing the stylus, here we go. Put this back in. We're measuring now the temperature of the water. And again, the temperature of the water should be the same as the temperature of the copper. And it looks like we are at about 99.3 degrees Celsius. Maybe 93, yeah, about 99.3 degrees Celsius. Okay, so we'll cool this back off to room temp, or at least to the water temp here. And now what I'm going to do is I'm going to dry this off. I'm going to remove the copper from the beaker, and I'm going to put it into this cup. And we're going to keep the cup very well insulated. So where's my styrofoam top? My cardboard top. Here we go. So we're going to insulate it, and we're going to put the temperature probe in and measure the temperature. And we're going to check to see what that final temperature should be. So this is now your chance to make a prediction. And again, my values here were approximated because I didn't know what we'd actually measure. So we're taking 114 grams of copper at approximately 99 degrees Celsius. We're adding it to an insulated cup containing 114 grams of water at approximately 22 degrees Celsius. When it is allowed to reach temperature equilibrium, what do you think that final temperature will be? Talk with a neighbor if you need to. What would you predict? If you feel you need to do some calculations, do some calculations. What do you think it will be? All right, let's get our answers locked in here, please. Give you about 30 seconds. About 30 seconds, get it locked in. About 15 more. And now we're going to count down. 5, 4, 3, 2, 1. And it looks like we're kind of all, yeah, it's kind of like a bell-shaped curve, isn't it? Very cool. All right, so now we're going to give it a shot here and see what happens. That's probably the most bell-shaped I've ever seen for this particular demo. So we need to go ahead and measure some temps. We're going to come out of here. We're going to go over to the Logger Pro. We're going to start collecting some data and get it to plot. And I need to get the temperature thermometer back in here, like this actually. And then we're going to go ahead and take the copper out of here. There's in one piece. There's 2 pieces. I'm going to make sure that they're entirely submerged. And we'll mix it up here. Again, we're going to go until the temperature reaches equilibrium. I don't need this heat anymore. This is one of the coolest things that I like to do. And you see where we're winding up. We're winding up at a temperature of 28.4 degrees Celsius, it appears. 28.4. Any ideas why we wind up, oh, and what was this temperature again? 99.3. And we were winding up at 28.4. Any ideas why we wind up so close to the temperature of water and not so close to the temperature of the copper? Go ahead, Phil.
Water takes a lot more energy to heat up than copper does.
Right. And not only does it take more energy to heat up, but it also takes, it's more difficult for it to give off that energy. Okay, so it has what's called a very high specific heat. So water has a very, very high specific heat, but it takes, again, a lot more energy to heat up the water than it takes to heat up some copper. And so it's something that involves what's called the specific heat capacity of the two, and water has a much, much higher specific heat capacity than does the copper. Now imagine for a moment that it's in the middle of winter and you have a couple benches that you're looking at. They're both the same size. One of them was a bench made out of a metal, another's a bench made out of wood, but let's say they're both about yay thick. You are having a choice to sit down on them. You're going to sit on the wood bench, you're going to sit on the metal bench. You're going to sit on the wood bench. Why? Well, it's going to feel warmer to you, and part of that, again, has to do with the fact that that metal has a very low specific heat. It's going to want to transfer that heat out of it very, very easily. It's very susceptible to changes in the temperature. So that heat is going to want to actually pour out of you and into the metal bench. So we are going to get back to this particular demo, save this data. This one we won't be using today. We're going to show this mathematically probably first thing on Monday. What we're going to do today is we're going to introduce a whole bunch of terms and look at some of the units and such for thermochemistry. This chapter here deals with energy, and we define energy as the capacity or the ability to do work. Capacity or the ability to do work. Now, if you've had some physics before, and I know many of you in here have, how do we define work? Work happens when you apply a force across a distance. So work is done when a force is applied across a distance. And again, energy is the ability to do work. So it's the ability to apply a force across a distance. But if we were to look at the formula for work, work then, by this definition, if we apply a force across a distance, that means that mathematically we calculate work by taking the force and multiplying it by the distance. And so if we're to define terms, W is work, F is force, and D is distance. And what we're ultimately trying to get to here is we're trying to figure out what are the units of work. Now, the units we can tell you is a joule, but what are those SI units? What is their origin? So to do that, we actually need to know what are the units of force, or how is force calculated? Well, again, if you go back to physics, a force is applied whenever a mass is accelerated. So force is equal to mass times acceleration. And again, if you need to define these, m is mass, a is the acceleration. Acceleration. You need to spell it right. So now, from here, we can go ahead and look at what those units are. If we look at the units of mass times acceleration, what are the SI units of mass? Almost. They are the kilograms. Remember, the SI units of mass are the kilogram. And the SI units of acceleration?
Meters per second.
Meters per second squared. So it's meters per second, which is actually meters per second squared. So these are the units of force. If we then come over here and say that these are the units of force, which is the kilogram dot meter per second squared, and then multiply this by the distance, what are the SI units of distance? Tough one. Meters. Good. So then we wind up with units of kilograms dot meters squared per second squared. And these here then are the SI units of work, which also happen to be the SI units of energy. So again, right here, these wind up being the SI units of work, which is also the same as the SI units of energy. And what we do then is we say that if we have 1 kilogram dot meter squared per second squared, we define this quantity as being 1 joule of energy, and we abbreviate the joule with a capital J. So again, by definition, these are what we have. Now you're going to find this definition on your conversion sheet. If you were to pull that conversion sheet out, you'll see this already. And we have that right down here. Again, part of the reason why I bring this up is that when you're going to be doing these calculations, you're going to want to try to cancel out units. And it may not be apparent how joules cancels out with the meters and seconds and everything else in there. So if you're going to want units to cancel out in your calculations, and you're using joule and you have meters and everything else mixed up, what you're going to have to do is instead change the units of joules to the units of a kilogram dot meter squared per second squared, so you can see exactly how those units cancel to come up with your answers. And so again, that's part of the exercise of why we go looking at these units here. Another set of units that we are going to use would be units of power. And we define power like this. We define it as being the energy exerted or expended per unit of time. It's energy expended per unit of time. So now we've already looked at what the SI unit, we need a formula, don't we? So basically this means that power is equal to, how do we calculate it?
J over S.
J over S, exactly. Because mathematically the word per means to divide. So the units of power then would be units of joules over seconds. And we say that a joule per second is actually 1 watt of energy, which we abbreviate with a capital W. Now some other units that we'll look at are the calorie. If we look at the calorie, we say that 1 calorie is defined like this. First of all, we abbreviate it as CAL. We say that it is the amount of heat energy necessary Anybody know where this goes? To do what?
Boil.
Not to boil.
To raise it by 1 degree.
To raise it by 1 degree. Raise how much? 1 gram of water. So it's the amount of heat energy necessary to raise the temperature of 1 gram of water by 1 degree Celsius. So again, this is how we define the calorie. Now, it turns out that you've probably heard of calories where? Foods, of course. And so if you think that this is the way that calorie is applied to food, it isn't. Turns out that the calories that we use for food are not calories, but they are actually kilocalories. And another way to write a kilocalorie is with a capital C, and so this is where case is going to matter, which is actually the same as 1 kcal, and this here is the nutritional calorie. So a nutritional calorie is actually a kilocalorie, which is then the same as how many calories? 1,000 calories, exactly. And then this becomes the amount of energy necessary to raise the temperature of 1 kilogram of water by 1 degree Celsius. And this also has a value, by definition, that's equal to 4.184 kilojoules. And that's because 1 calorie is the same as 4.184 joules. And this right here is an exact relationship and is one that you are going to find also on your list of conversions on your conversion table. So again, you don't need to memorize it, but again, this here is an exact conversion that allows interchangeability between joules and calories. So any questions with this intro piece here? Okay, next up, we're going to look a little further at the distinction between kinetic energy and potential energy. Kinetic energy and potential energy. Kinetic energy is the energy associated with motion or movement. And potential energy we can think of as being stored energy, or it's energy based on position. So again, kinetic energy is the energy associated with movement, and potential energy is energy that's stored based on position. Okay, so now the way that we calculate kinetic energy is like this. And I think we've seen it before. It's equal to 1/2 mv squared. Remember now that m stands for mass and v stands for, do you remember what that is? It doesn't stand for velocity, it stands for speed. Because of course if it's velocity, not only must it have magnitude, but it must also have direction. So velocity is actually a vector quantity. So V actually stands for speed. So now when we look at the units, if we were to do a quick unit analysis, let's see what we wind up with for units on kinetic energy. Remember again that the SI units of mass are the, what are the SI units of mass? Kilogram. And what are the SI units of speed? Meters per second. And so now if we're squaring this, because it's speed squared, that tells us that the units on here are going to be a kilogram dot meter squared per second squared, of course, which once again are units of energy or work. So we're showing here now that these units do in fact match. So again, part of the reason why we go through this exercise of looking at this is to remind ourselves that even though we may be using units of joules, 1 joule is the same as a kilogram dot meter squared per second squared. If we went and looked at potential energy, the way that we calculate the potential energy is like this, mgh. And in this formula, m again is the mass. What do you suppose g is? That's the gravity. So this is the acceleration of gravity. Acceleration of gravity. And then h would be the height. So what this is basically telling us is that the water behind a dam is going to be most useful if that dam is of a greater height. That's why we don't build just little dams. If we're trying to get energy out of it, we build a very tall dam. So now, if we want to look at the units on this, we should remember that the units of mass are the, again, kilogram. Acceleration of gravity, meters per second squared, because again that's the acceleration units. And then we multiply that by height, which the SI units are meters. If we go through all of this, we see that the units still are the kilogram dot meter squared per second squared, which of course 1 kilogram dot meter squared per second squared is the same as 1 joule. So again, depending upon which formulas we wind up using, in the end, this kilogram dot meter squared per second squared, if we wind up seeing it, that's the joule. Likewise, if we're using joules, we have mixed units with kilograms and distances and whatever else. It's going to be useful to express the units of joules in these SI units to help us figure out what the units are in our final answer. Now, another thing here that we work with in this chapter a whole lot is the law of conservation of energy. And the law of conservation of energy is worded a whole lot like the law of conservation of mass. When we looked at the law of conservation of mass, we said that mass or matter can neither be created nor destroyed as a result of a chemical change. We say the same thing when we look at chemical reactions about energy. You can neither create energy nor destroy energy as a result of a chemical reaction. Now that's going to work well for us this semester. However, when you get into second semester, or if you've had some physics before, you're going to find out that we've actually been lied to a little bit. Because really, there's an equation from Einstein that says E is equal to mc squared. And what this tells us is that mass can be converted into energy, or energy can be converted into mass. But this is of insignificance in chemical reactions, because in chemical reactions these take place out in the involve the electrons, and so the changes in mass that might be observed would be so small we can't detect it with the instruments that we have available in here. However, if we go to looking at what happens in the nucleus, all of a sudden this becomes very significant, and is the basis behind nuclear energy and atomic bombs and such. That we'll find, and this will be second semester of this course in Chem 1062 when you take it, and it's the very last stuff you cover in there. Then you'll talk about energy and mass interconvertibility. But in there then, what we should really be talking about is a combined conservation law, is that the total amount of mass and energy remains constant. But at least when we look at chemical reactions, the way we deal with it, in here we confine our work to the electron cloud. The law of conservation of energy works very well. Now, a term that we're going to be using a whole lot in here is a term called internal energy. And we label internal energy with the letter E. And we define the internal energy as being the sum of the kinetic and potential energies of a substance. The sum of the kinetic and potential energies of a substance. We say that the internal energy E is both of these things. We say that it is an extensive property, and we also say that it is a state function. So internal energy is an extensive property, and it is a state function. And here's what these things mean. If we say that something is an extensive property, that means that the amount matters. The amount of something we have matters. Can you think of something where the amount of something matters? What is a property? I don't know if any of you have been observing what's happened to me this semester, but I've lost 20 pounds since this semester started. And so that's something that would be an extensive property, weight or mass. Okay? And so I notice it when I look in the mirror, but I also notice it when I jump on the scale. And so that would be an example of amount matters. I can feel it when I run up and down the stairs. Okay? So again, that's an extensive property. But internal energy is also an extensive property. If you want to travel further in your car, I mean, you can get a more fuel efficient one, but if your car stays the same and you want to travel a lot further, what do you need to do? More gas, exactly. So energy here is going to be an extensive property, because again, if we want more energy, we have to use more stuff. The amount matters. We talked about a state function here. A state function is one which only the state you're currently in is important or relevant, or the state that you're going to is relevant. So either the state you're in or the state you're going to is relevant. And by that means, let's say that I want to climb a mountain, okay, a really tall mountain. If I want to climb a mountain, there's multiple ways to do it, but the way I do it doesn't matter. I can climb a mountain by going straight up. First, if I go straight up, how much effort is it going to take to go straight up? A lot of effort. Another way to do it might be to kind of go around like this. It's going to require less effort, but it's going to take more time. Okay? But in the end, it doesn't matter how you get there, whether you go straight up or whether you go round and round and round. All that matters is where you start and where you end. And nothing else matters when something is a state function. So that's what internal energy is. Only the current state or where you're headed matters. Another thing we'll look at, and again, we're just throwing a lot of things out here, we're going to be using this symbol a whole lot. What should we call this? Not a triangle, we call it delta. And if we see delta, delta means to do what mathematically? Add, subtract, multiply, divide, what is it? It means to subtract. It means to subtract. And it's even a little bit more specific than that. It always means that you're going to take the final state and subtract from it the initial state. And so we're going to look at the change in internal energy, which of course is going to be the final internal energy minus the initial internal energy, to see what happens. So again, whenever you see a delta, this always means to take the final state minus the initial state. And the reason for that is because we're going to start assigning signs to them, either positive or negative. In fact, signs aren't going to be implied when we use delta. We always want to show the sign, even if it's positive. And the reason for that is if we show a positive sign for the answer, what does that tell us about the final energy state compared to the initial?
Greater.
Means the final energy state is greater than the initial. In other words, it means that the values have increased. And if we see a negative sign for this, that means that the final is less than the initial, and that means that the values would have decreased. So we're going to apply signs to things to help tell us what happens. And because of that then, if we want to apply this to a chemical reaction, in a chemical reaction, the end is what we call the products of the reaction, and the beginning is what we call the reactants. So at the very end, in fact, we're going to see a whole bunch of formulas where the convention is going to be to take the products minus reactants. If you want to know why the convention is always products minus reactants, convention is products minus reactants because products are the final state, reactants are the initial state. So then, going back to our reactions, let's look at this particular reaction. Again, this is a day one reaction that we did in here of hydrogen reacting with oxygen to make H2O in the gaseous phase. Once again, this reaction is one that is it endo or exo? It's an exothermic process. So if it is an exothermic process, we should then be able to make a plot in which we plot energy, that is the internal energy, versus time. Now by definition, again, an exothermic process is one that does what?
Releases heat.
Releases heat. So it releases energy to the surroundings. If it releases heat, that means it starts where? It starts high and winds up low. So on the plot here, we start high, we end down low. This over here is your hydrogen and oxygen gas, and sitting down below here, this is your water in the gaseous phase. And then this distance right here between the two is what we'd label as the change in internal energy, the delta E. And this would tell us that delta E has a value that is which sign?
Negative.
It's going to be negative. The sign is negative because we end at a low value, we start at a high value, a small value minus a large value is going to give us a value that is negative. Any questions?
So, on the equation, would it really be 2H2O plus heat?
Because heat is a product, if we want to show it in action in the reaction, yes. We would write the product out here as heat. Okay, very good. Anybody else? But what we'll find is we're going to be giving labels that we assign signs to, either positive or negative at the end. Okay, anybody else? But yeah, if we would write it in, we would think of it as heat. Okay, then let's look at an endothermic reaction. Now you don't need to rewrite this whole thing, I'm just going to do it because I can do it fast. This is the one that we looked at here at the beginning of the hour, or end of the hour I guess, last class period, between the barium hydroxide octahydrate and the ammonium chloride. And remember, this was ambiguously phased. Then we had ammonia, also ambiguously phased, and then there was the H2O that we produced out here as a product. Okay, and then we balanced it something like this in here. And once again, this was an endothermic process. So now, in an endothermic process, which this one is, we can then make a plot of the internal energy versus time. We make a plot of the internal energy versus time, and it's endothermic. Remember, endothermic now is, by definition, a process which absorbs energy from the surroundings. Well, if it absorbs energy from the surroundings, that means that energy is going to start where? Low, and it's going to wind up high. So we put it in here, start down low, we wind up high, and rather than rewrite all this stuff here, I'll just put in reactants down below here, products up above. And then if we were to look at this distance right here, this of course then is going to be delta E once again, and the sign on delta E is going to be one that is positive. Because again, we have a larger value at the end than we had initially, and so delta E will be positive when the process is endothermic. So in the end, what we're going to say is this. First of all, the change in internal energy would come like this. We'd say it's going to be equal to the heat transferred by the system plus the work done by the system. And this all goes back to the original definition of what internal energy is. Internal energy, we said, is the sum of the kinetic energies and potential energies that are involved. And so we want to look at it like this. First of all, in terms of symbols, and don't ask me where we come up with all these symbols, the symbol for heat is Q, and the symbol for work is W. And if we were to envision this now, again, this is kind of where we started today. We can talk about the system, and we can talk about the surroundings. The system and the surroundings. And between the system and the surroundings, we can have transfer of heat that occurs, which again we label with the letter Q. We can also have the transfer of work that occurs, which again we label with the letter W. The way heat transfers perhaps is more apparent because we could look at, just like we did with the copper and the water here, how heat transfers from one out of the other. But work can also be transferred as well. If, for example, you were to consider This maybe being the cylinder in a car engine. If this is a cylinder in a car engine, what happens is that fuel is injected into the cylinder. It gets ignited when it combines with air. When this mixture of fuel and air gets ignited, what's going to happen to this volume inside of here? It's going to expand, because as it explodes, it'll cause this expansion. Well, as it expands then, this is going to push up, and in your engine it pushes up against something called a camshaft. If you have a bunch of cylinders in here, that camshaft winds up spinning around, and eventually as it spins around and it's hooked up the gears, hooked up the wheels, that's ultimately what causes those wheels to turn around. So it's continual explosions that occur in here as that camshaft turns around in there that ultimately wind up powering the system. And so there's a transfer of work that goes from the system in here to the surroundings, which would be like your wheels or whatever that are part of that automobile. So ultimately at the end, what we say is this, and of course my stylus is gone, here we go. The signs on the system and the surroundings are going to be just the opposite of each other. So we're going to say that the change in internal energy for the system is equal to negative the change in internal energy of the surroundings. And as we label these items here, we might talk about the change in internal energy of the system. That's going to be this one right here, that'll be this one, and this one here. All of these here represent the change in internal energy of the system. Now sometimes we add subscripts when we want to distinguish between the system and the surroundings, like we did here. We want to re-emphasize the fact that the sign on the system is just the opposite of what it is of the surroundings. As of course, if the system gives off energy, that must mean that the surroundings would have gained energy. If the system gives off work, that means that the surroundings would have taken in work or used that work. So when we leave the subscripts off, like we do here, it's always implied that these refer to the change in internal energy of the system. Now when we start in here on Monday, I'd hoped that we'd get to this today. It looks like we didn't. I don't want to keep you over. When we start in here on Monday, here's where we're going to start. We're going to start by looking at sign conventions. We're going to start by looking at sign conventions. And by sign conventions, we want to look at what does it mean if we have a sign on delta E that is positive or negative? What does it mean if we assign a positive or negative sign to Q? What does it mean if we assign a positive or negative sign to W? So we'll kind of make the shell to get us started here. The sign on delta E and Q and W can all be positive or negative. And so on Monday in here when we come in, we'll talk about what does it mean is happening when we see a positive or negative sign on these values. Any questions that you have?